Alright, so I'm about to do the beginning of section 1.2. Just like section 1.1, section 1.2 will be broken into two videos, so I'll call it the first part. And the first part of section 1.2 is going to involve calculating limits using algebra. That are not at infinity. And the second part of this section, you'll be calculating limits, for the most part using algebra. Probably calculate. We'll do a bit of tables in the second part too, but mostly algebra. That's what's going to make its way onto the test anyways, that are at infinity. And they're completely different. Calculating a limit that's not at infinity is very different than calculating a limit at infinity if you're using algebra. If you're using a graph to find a limit or a table to find a limit, then limits at infinity and limits that aren't at infinity are more or less the same. When I'm asked to find any limit that's not at infinity using algebra, my first stab is to take the value of x I want to find the limit at and plug it into the function. If I plug it into the function and I get something other than undefined, then that's what the limit's going to be. The first chunk of problems, because they're not fractions, I'll be able to find the limits perfectly well by just plugging the number in for x that's given in the problem. Once I get to the fraction problems, there's kind of three kinds of fraction problems, and I'll talk about those when I get to them. So the first problem that I'm going to do is problem 2. Then after I do problem 2, hopefully you can do problem 1. I want to find the limit as x approaches negative 3 of the function 5x minus 7. Well, I can find that simply by plugging in negative 3 for x and doing the algebra. Once I plug the negative 3 in for x, I stop writing the word limit, because I'm actually finding the limit when I plug the negative 3 in for x. So this tells me that the limit as x approaches negative 3 of the function 5x minus 7 is negative 22. For my answer, I can just write the number negative 22, or if I want to write something that's maybe a little more elegant, I could write the original problem, the limit as x approaches negative 3 of the function 5x minus 7 equals negative 22. That's all I need to do for problem 2. That's all you would need to do, something similar to that for problem 1. If you wanted to confirm your answer by graphing, I can certainly do that. But in order to confirm my answer by graphing, I'm going to have to set a window so it makes it easy to see the limit. So what I'm going to do, I notice that I wanted to find, so I'm going to graph this function eventually on my calculator on y1 on my calculator. I'm going to enter the function 5x minus 7. And in order to be able to calculate the limit using my calculator, I need to set the window so that it covers x equals negative 3 very nicely, but not too broadly. So I'm going to set my window to have an x min and an x max that are, my x min has to be less than negative 3, my x max has to be bigger than negative 3, but I don't want to be too far from negative 3. So I'm going to make my x min negative 4, which is less than negative 3. my x max, which is negative, I'm going to make negative 2, which is bigger than negative 3. So that will get the x part of my window narrow enough so it's going to be easy to find the limit, but it won't get me there all the way because I don't have the good y's. My y's need to capture what the limit is. If my limit is correct here, if I set my y-win and my y-max to cover up negative 22, I should see when I see the graph, I should be able to see the limit clearly. So I'm going to make my y-min something less than negative 22, like maybe negative 23, and my y-max something bigger than negative 22, say maybe negative 21. If I graph this function with this window, I will be able to use the trace feature on my calculator to find the limit. In fact, I think because of the way I'm setting up the window, that the limit's just going to pop out. But I'll show you anyways what I mean. So I'm going to clear out anything that I have in my calculator that I was using for graphing for some other problem. And I'm going to enter the function 5x minus 7. And if I did a graph of this is just going to be the graph of a line. Usually when I graph, I just hit the zoom button and then go down to option 6 and set standard. Unfortunately, that window won't make it so I could find the limit that I'm looking for because the y's don't go down far enough, and maybe the x's are a little broad, because what it does is it sets the x's from negative 10 to 10 on the min and the max, and the y's from negative 10 to 10 on the min and the max. The x's, it does cover the negative 3 that I was trying to find the limit at. I could technically find the limit without changing the x's, but I couldn't find the limit without changing the y's because the y's aren't close enough. They don't capture the negative 22. So now I'm going to set the window to what I said I'm going to set it to. So I'm going to make my x min negative 4 by using the negative on the bottom row of the calculator. Then hit enter. X max is negative 2. I always leave the x scale at 1. I think that's how it makes marks on the axes. I never change that ever. And I'm not really 100% certain what it does if I do change it, but I'll never take it off of 1. My y min I'll make negative 23, my y max negative 21. I leave the y scale and x resolution at 1 always. Again, I'm not completely sure what those do, but they're not important what they do or don't, won't impact what this how I'd find my limit. So now I'm going to hit the graph button with this window, and it's just going to show me a little segment of the line. To find the limits with your calculator, you need to trace, and if you could trace and get your calculator to say what have the x value that you're trying to find the limit at, then the corresponding y value will be the limit. So when limits exist and you set your windows properly, you can see what the limit is by just tracing to the x value. So I could trace using the left arrow or the right arrow, and here I could see that the limit exists. The left-hand limit is going to be the left-hand limit is negative 22, the right-hand limit is negative 22. By that picture, and based on what we did in section 1.1, I can tell the limit is negative 22. Because the halves of the graphs are connected, I can tell the limit exists, and it is that y value of negative 22. Hopefully that's good enough. I won't do much graphing on this section, except when I think something is new and interesting, and then I'll break out the graphs. For the most part, I'm going to do the limits using algebra, because that's what the instructions say. So hopefully, with how I did problem 2 in black, you can find the limit for problem 1. You don't need to do any graphing to confirm your limit unless you just really feel the need to do the graph. You can probably work ahead and do problem 3 and problem 5 just fine, because the algebraic strategy for finding the limit will work the same that I did in problem 2. So to find the limit as x approaches 2 of the function in problem 4, always my first step is just attempt to plug in the value that's given for x in for each of the x's. If I get a value that's anything other than undefined, then that's what the limit's going to be. So So I plugged in 2 for the x's. Now I'll do the orders of operations. 2 squared is 4. 3 times 2 is 6. Minus 7 is minus 7. 4 minus 6 is negative 2. Minus 7 is minus 9. So my answer to number 4, I can either write just negative 9 by itself, or if you want to be, more, something that looks in some sense better, you can write the problem with the answer. One thing that's semi-important is once I plug the number that I'm asked to find the limit at in for x, I stop writing the limit. That's called taking the limit. Once I take the limit, I don't write the limit anymore. So once the x's disappear, none of my algebra is going to have the word limit anymore. So you should be able to do the same thing for number 3. And I'll move on to the next page, which is going to contain 5 and 6. I'll still be able to do them the same way. So even though it's a square root, if the number that I'm asked to find the limit at is in the domain of the square root, then just plugging in the value for x that I'm asked to find the limit at in for the x will be the best way to find the limit. So until we get to fractions, finding the limits using algebra is pretty straightforward. Once I get in the world of fractions, then it gets to be a little bit trickier, because there's kind of 3 cases when we're finding the limits with fractions that we'll have to deal with. So I'm just take the negative 3, I plugged it in for x. Now I'm doing the orders of operations. I don't need my calculator to do this, but you certainly can use your calculator if you want to. So again, if you feel the urge to write the problem next to the answer, that's completely fine, but you just need to write what the limit is. You don't need to write the problem next to the answer. And again, once I plugged the negative 3 in for the x, I stopped writing the limit, and then I wrote a string of equal signs implying that everything in this row they're equal to each other. So this line is equal to that line is equal to that line. And it's just kind of nice algebra. If you get lazy and don't put the equal signs, sometimes I do that. I'm not going to take points off for that. So up through 6, we don't have fractions. There's really no worry when we're finding the limits at a number other than infinity when it's not a fraction. Once we get to fractions, there's kind of 3 cases, and the best case scenario of finding the limit at a fraction is what problems 7 and 8 are. If you're asked to find a limit of a fraction, I'm going to approach that limit just like the limits that I've done so far. If I can plug a number in for x and I don't get undefined, then that's what the limit's going to be. So just like I did 2, 4, and 6, I'm going to try to do 8. In fact, anytime I'm asked to find a limit at a non-infinite number, my first step is to plug that number in for x, and if I get something other than undefined, that's what the limit's going to be. When I plugged in 4 for the x's in this problem, notice in the denominator I didn't put the 4 in a parentheses because the x wasn't multiplied by anything, nor did it have an exponent. But when I plugged in 4, I got a fraction, and that's not undefined, so that's what the limit is. So my answer to number 8 is going to be 9 over 11. And again, you can write the problem next to the answer. The rest of the problems that have limits with fractions are going to be less straightforward, and I should speak about that. Maybe I'll do an example. Here's an example that's just not from the handout. So find the limit. I better make up something decent here. X squared plus 5x minus 6 over x squared minus 1. So I'm going to do 2 problems. I'm going to do the limit as x approaches positive 1 of this fraction, and I'm going to do the limit as x approaches negative 1 of this same fraction. And these will illustrate the two things that can happen when I'm finding the limit of a fraction and my algebra gives me something that's undefined. So the case 1 here, in case 2, will illustrate the two bad things that can happen when I'm finding the limits of fractions. So case 1, finding the limit as x approaches 1, so I'm going to go plug in 1 for x, which is going to be 1 squared plus 5 times 1 minus 6 over 1 squared minus 1. If I do the orders of operations, the numerator you get 1 plus 5 minus 6 over 1 minus 1. And that comes out to 0 over 0. If you're trying to find the limit of a fraction and you get 0 over 0, which is undefined, there's likely algebra that I can do to make the limit appear. So this limit will exist. We'll say likely exist. In our class, it'll definitely exist. And I'm going to have to do some algebra to make that limit pop out. And in this particular problem, the algebra is going to be factoring and canceling. Before I finish that problem up, I'll show you the other thing that can happen for this same fraction, but at limit at a different value of x. So if I was trying to do case 2, first thing I do to find a limit as x approaches negative 1 is plug in negative 1 for x. And I'm going to get negative 1 squared, which is positive 1, 5 times negative 1, which is negative 5, minus 6. The denominator, negative 1 squared, is positive 1. So I'm going to get negative 10 over 0. This is also an undefined fraction, but it's not 0 over 0. When you're trying to find a limit of a fraction and you get undefined, 0 over 0 is a good undefined, meaning you could do algebra and that algebra will help you point you to the limit. If you get a number over 0, then this limit won't exist. And there isn't any amount of algebra I can do to make that limit occur. So the answer to number 2 I'm done with. There isn't going to be anything more I have to do to case 2. When I'm finding the limit of a fraction, if I get a 0 in the denominator and I don't get a corresponding 0 in the numerator, then that limit doesn't exist. If I'm trying to find the limit as x approaches some number of a fraction and I get 0 over 0, then that limit likely exists. There's two algebra tricks that we'll learn, and the easier of the two is factoring and canceling. The harder of the two is multiplying by conjugates that we did in the end of the last section. So I'm going to finish up this limit right here. So I got 0 over 0. That isn't what the limit is. In order to find out what the limit in this case 1 actually is, I'm going to need to factor and cancel. I'm going to factor the numerator. The numerator factors into x plus 6 times x minus 1. The denominator factors into x plus 1 times x minus 1. And now I'm going to cancel. And when I do that, I get the limit as x approaches 1 of x plus 6 over x plus 1. And now I'm going to attempt to plug the 1 in again. And when I plug the 1 in this time, I'm going to get 7 over 2, which is 3.5. So my answer to case 1 is 7 over 2, or 3.5. Or I could say the limit as x approaches positive 1 of x squared plus 5x minus 6 over x squared minus 1 is 7/2. I want to show you real quickly, even though it's taking a long time, on my calculator, the difference between case 1 and case 2. So I'm going to do some graphing to show you that the limit of case 1 is, well, 7/2, which is 3.5. And quite honestly, my calculator doesn't do a stellar job with decimal or fraction limits, but I'll go ahead and do it. So to show you that the limit of case 1 is 3.5, I'm going to graph the function x squared plus 5x minus 6 over x squared minus 1, and I need to make my window good. And to make my window usable, I need to take my x's and make them cover up 1, because that's the value that I'm trying to find the limit at. So I'm going to make my x min less than 1, which is 0, my x max bigger than 1, which is 2. Since the limit is 3.5, I'm going to make my y min less than 3.5, which is 3, and my y max bigger than 3.5, which I'll do 4. If I graph this function with that window, it's going to show me that the limit is 3.5, and I won't be able to trace to it like I was able to trace to the limit for the other problem, because the graph is going to have a hole here, and the hole is going to make it so I won't be able to see the 3.5 exactly, but I'll be able to show that the limit exists and it's about 3.5. So I'll turn my calculator back on, hit my y equals, clear this, then do parentheses x squared plus 5x minus 6 parentheses divided by parentheses x squared minus 1. Again, if I just did zoom standard, it would give me a better graph than the window that I'm about to show. So this is kind of what the graph really looks like, but this version of the window makes it hard to find the limit. So I'm going to tighten up this window. I'm going to make my x min 0, my x max 2, my y min 3, my y min 4, and when I hit graph, it's going to show just the segment of the graph that I'm trying to find the limit at, and there's going to be a big old hole in it. And this is the point x equal 1, y equal 3.5, where that hole exists. When I hit my trace function, what it does is it goes right to that point, but it doesn't have a y value because the function isn't defined there. That's why I got 0 over 0. When you get a 0 in the denominator, the graph doesn't exist there. If the graph doesn't exist in a fraction, there's either an asymptote or a hole. And in this case, there was a hole. So I'm going to hit my trace button. If I trace just to the left of that hole, I see the y is 3.52. So that means that's kind of an upper bound on my limit. And if I hit my trace button and trace to the right, I get 3.47. So the best I can do with this window in my calculator, because the limit is right there, the y value of that point, the limit is somewhere between 3.47 and 3.52. And so the answer that I got by hand at 3.5 makes complete sense, that the y coordinate of that point is bigger than 3.47, it's less than 3.52, so it makes complete sense that the limit would be 3.5, and it exists. You can tell the limit exists because the graphs, if I just filled in that point, the graph would be connected through that point. So there's one case. That was the case 1. If I moved on to the case 2, where the limit doesn't exist, well, if I wanted to graph that on my calculator, window that's appropriate, and the window that's appropriate has to have an x min that captures -1, and our x min and x max that captures -1. I might make my x min -2 because that's less than -1, my x max 0 because that's bigger than -1. So the x's are easy to decide. The y's aren't so easy to decide because the limit doesn't exist. There isn't any right nor wrong y. So I'll just make my y min and my y max just the standard -10 to 10. Quite honestly, it won't matter at all what y's you choose. when you go to find the limit here, because it doesn't exist. So I have the function in, it's the same function. I'm going to tweak the window to go from x equals -2 to 0, and I make my y's -10 to 10. And now when I hit graph, heck, look, the graph, this is 1, and the left-hand limit is some number way, well, it's actually negative infinity. The left-hand limit is down here somewhere on the graph, and the right-hand limit is up here somewhere on the graph. The left and the right-hand limit, they don't equal each other because the graph doesn't connect through x equals 1. So because the graph isn't connected through, this is x equals -1 right here, should I say, because the graph isn't connected on either side of x equals -1, let me make the window a little bit bigger. On the y's, maybe I'll make the y's -100 and +100 to illustrate that more. So here's x equals -1. The left-hand side of the graph plunges down. The right-hand side of the graph plunges up. It's actually the left-hand limit is like negative infinity. The right-hand limit is positive infinity. Neither limit exists. And because at -1 the graphs don't connect, the whole limit doesn't exist. So the important thing so much isn't understanding the graph. It's understanding that if I'm trying to find the limit of a fraction, if I get 0 over 0, then there's likely some algebra to do to pull that limit out, and it likely exists. But if I get a number over 0, then the limit doesn't exist, and there isn't any bit of algebra that I could do to make that limit pop out. So now I'm going to do the rest of the problems in the section that have limits that aren't at infinity using algebra. So problem 10, it's a limit that's not at infinity, so I can always just plug the value in for x that I'm given. And best case scenario is that I don't get a 0 in the denominator. If I don't get a 0 in the denominator, then I know what the limit is. Let me do the algebra here. So I plugged 1 in for all the x's. The numerator, I get 1 plus 4 minus 5 over 1 minus 1. That comes out to 0 over 0. When you get 0 over 0, the limit likely exists. And the strategy for making that limit, finding that limit in this case, is going to be factoring and canceling. So I'm going to improve my chances of finding the limit for number 10 by factoring the numerator, and that factors into x plus 5 times x minus 1. Hopefully your factoring skills haven't deteriorated too much. And the denominator factors into x plus 1 times x minus 1. If you can't factor, stop in and visit me. I can show you some videos I have on factoring, or I can reteach you factoring. But I'm not going to explain factoring in the video because the video is already long enough and boring enough. You don't want to see that. So what I've done is I've factored, and I've canceled out the thing that was causing the 0 over 0 to happen. Now I'm going to plug the 1 into the reduced version of this. I'm going to get 1 plus 5 over 1 plus 1, which is 6 over 2, which is 3. So the limit as x approaches 1 to this fraction is going to be 3. And I'm not going to rewrite the original problem next to the answer. So problem 9 should work just like this. So you should be able to do 9 just fine now. You might be able to do 11 as well. You might be able to do 11 without me doing 12, but let me do 12 and maybe that will get you unstuck. But if you can do 11 without watching me do 12, then that's good. Just fast forward through my explanation of 12. But always, when I'm trying to find the limit of any function, I always take the value that's given for x and plug it in, because if I get something that's defined, then I'm done. That's what the limit is. In a fraction, if you get 0 over 0, that's kind of the worst case, because then you have to do algebra. Really? That surprised me. So on my problem 12, I plugged in negative 2 for my x's. I got negative 2 squared minus 4 over negative 2 squared minus 3 times 2 plus 2. This is going to have a 0 in the numerator and 12 in the denominator. That's not a bad thing. Fractions that have a 0 in the numerator are completely fine as long as they don't have a 0 in the denominator. 0 over 12 is equal to 0, and that's what the answer to this is going to be. So this limit actually exists. So the only time I have to do algebra on a fractions limit is if it has 0 in the denominator. If the fractions limit, when you plug the number in, gets 0 in the numerator, then that limit exists and it's 0. I don't think that's the case for number 11. I think in number 11, you're going to have to factor and cancel to do yours. I think you're going to get 0 over 0, and when you get 0 over 0, then you've got to factor and cancel or do some other algebra. But mine was easy because I don't have to go through the factoring and canceling because I didn't get a 0 in the denominator. If you're trying to find the limit of a fraction and the number that you get when you evaluate it at the value of x that's given, if it's something that's defined, then that's what the limit is, and 0 is an acceptable value for a limit. 14 is really unfortunate because it's going to require bottoms-up factoring, or factoring that's, harder than usual, but we're in calculus, so we should be able to handle some, harder factoring. But maybe I'll get off lucky in problem 14 and just be able to plug in and be done. So I plugged in the 3's for the x's because that's what I'm finding the limit at. Now I'm going to do the exponents first. So I get 2 times 9 because the 3 squared is 9 in the numerator. I'm limiting the amount of algebra that I'm doing on a step just so you can follow, but you can certainly do more algebra than me. So first step, I plugged in 3 for the x's. Second step, orders of operations require me to do exponents. Third step, I'm going to do the multiplication. 2 times 9 is 18. 7 times 3 is 21, so I have the negative in front of it. In the denominator, 3 times 9 is 27. 7 times 3 is 21, minus 6. This comes out to 0 over 0. That's really unfortunate because fractions, when you get 0 over 0, you likely can rewrite the problem to make the limit exist. In order to pull this limit out, I'm going to have to factor both the numerator and the denominator. And because you might be rusty on this kind of factoring, I'm going to do bottoms-up factoring. I'm going to do it off to the side just to show you, just in case you've forgotten how to factor something like this. So bottoms-up factoring, the first step is going to be to multiply. Kind of the a and the c are the outer numbers. So that multiplies, and I change the problem to x squared minus 7x plus 6. Second step after you do the multiplying is you factor what is remaining there. That factors into x minus 1 times x minus 6. And then I divide, reduce, and bottoms up. It's kind of, I do them all in one. Since I started off multiplying by 2, I need to end up dividing by 2. The first fraction's not reducible, so I bottoms up it, and that turns into a 2x minus 1. Second fraction is reducible, so I reduce it and I get an x minus 3. So that's this numerator. I'm going to be able to change it to be 2x minus 1 times x minus 3. I need to do the same thing for the denominator. You don't have to do bottoms-up factoring if that's not how you learn how to factor these kinds of trinomials, but most students at some point that's what they learned. So I also need now to factor 3x squared minus 7x minus 6. And again, if you have another strategy for factoring these, that's fine. Just bottoms up is what most students wind up doing. So I'm going to multiply the 3 and the 6 and get x squared minus 7x minus 18. I'm going to factor that, which factors into x plus 2 times x minus 9. And then I'm going to divide, reduce, and bottoms up. I started off multiplying by 3. I'm going to divide by 3. First fraction doesn't reduce, so I bottoms up and get a 3x plus 2. Second fraction reduces, so I get an x minus 3. So now I'm able to rewrite the original denominator as 3x plus 2 over x minus 3. So I'm able to take the original problem that was unfactored that gave me this nasty 0 over 0, and I'm able to factor, and once I do the factoring in both the numerator and the denominator, the factor that made the 0 happen will disappear, and I can continue my algebra by taking the reduced fraction. So now I can rewrite this problem as a limit as x approaches 3, and then in the numerator I'm going to have a 2x minus 1. In the denominator I'm going to have a 3x plus 2. And now I'm going to attempt to stick that 3 in. And I'm going to get 2 times 3 minus 1 over 3 times 3 plus 2. The numerator is going to be 6 minus 1. The denominator is going to be 9 plus 2. Now I don't have a 0 in the denominator, so my answer is going to be what the limit is. And my answer to problem 14 is going to be 5 over 11. Really, the hard part of that's the factoring. Immediately when I get 0 over 0, I know the limit likely exists, and I have to deal with some algebra. And factoring and canceling is the algebra that you do when there aren't square roots sticking around in the problem. So hopefully you can make a stab at 13. It's going to be the same thing. You're going to have to factor the numerator, factor the denominator. You're going to cancel out the factors of x minus 2s, and you'll plug the numbers in. 15, 16, 17, 18, 19, and 20 all have square roots in the numerator. And whether I have square roots in the numerator or not, when I'm trying to find any limit, my first step is to take the value of x that I'm given and I'll plug it in for x, because it's going to tell me either what the limit is or if I have to do more algebra or not. So square root of 49 is 7. This gives me 0 over 0, so there's likely, the limit likely exists, and there's likely algebra that I need to do to find that limit. The algebra that I need to do to find the limit for this problem can't be factoring and canceling because neither the numerator or the denominator factors. The algebra that I need to do to find this limit is the algebra that we did right at the end of section 1.1, and it's multiplying the numerator and the denominator by the conjugate of the numerator, which is, the conjugate is just the numerator with its sign changed. And when we're finding this kind of limit, the numerator we FOIL, the denominator we leave alone. So my next line, I should probably write equals because this equals the line above it there. My next line, the denominator isn't going to change a bit. It's going to stay x minus 49 times the square root of x plus 7. But the numerator, I'm going to do the work. I'm going to do the FOILing. So in the numerator, so I'm going to multiply this out here. First, our square root of x times the square root of x, which are the square root of x squared, which is just x. Outers are the square root of x times 7. That's positive 7 square root of x. Inners are minus 7 times square root of x, which is minus 7 square root of x. And lasts are minus 7 times 7, which is minus 49. When you multiply by conjugates, the outers and the inners always cancel. And generally, when I'm multiplying conjugates, I only multiply the first and the last. I don't even show the outers and the inners. So what I'm going to have left when I fill out the numerator is x minus 49. That's a good thing because that's going to help me cancel and cause the zeros to disappear when I plug the 49 in. So I'm going to cancel. I've canceled the entire numerator. I can't write a fraction without a numerator, so I leave a 1 behind in the numerator. And in the denominator, I won't need the parentheses anymore. I just have the square root of x plus 7 left. I'm going to plug now in 49 for the x. I'm going to get 1 over 7 plus 7 because the square root of 49 is 7. And my answer to problem 16 is the limit of that function as x goes to 49 is 1 over 14. do 2 more of those. You can try 15 now. You're going to multiply top and the bottom by the square root of x plus 4 over the square root of x plus 4. 17 and 19 have exactly the same trick, so you might be able to, if you got 15, you could do 17 and 19 without watching me do 18 and 20. Well, I'll go ahead and do 18 and 20 just so you have more in your notes. So for 18, first step of finding any limit is to take the value for x and plug it in. This gives me 8 minus 8 over 0, which is 0 over 0. When I'm trying to find the limit of a fraction, if I get 0 over 0, there's likely algebra I can do to make that limit pop out. The limit usually exists. And in the 3 problems that we have that have a square root in the numerator of a fraction, the big trick is to multiply by the conjugate of the numerator. So I'm going to multiply the numerator in my problem by the square root of x plus 8. And I'm going to multiply the denominator by the square root of x plus 8. The numerator, I'm going to FOIL out. The denominator, I'm just going to leave and not multiply it out. So I'm going to leave the denominator 6x minus 64 times the square root of x plus 8. And in the numerator, I really just have to do the first and the last because the outers and inners are going to cancel. So the first are the square root of x times the square root of x, which is the square root of x squared, which is x. The last are minus 8 times 8, which is minus 64. And that's exactly what the numerator will FOIL to. Again, I didn't do the outers and inners because they would cancel anyways. Now I'm going to cancel the x minus 64s. I can't write a fraction without its numerator, so I'm going to leave a 1 behind in the numerator. And in the denominator, I'm going to have the square root of x plus 8. I'm going to plug in 64 for x. I get 1 over the square root of 64 plus 8, which is 1 over 8 plus 8. So my answer, the limit of this, is going to be 1 over 16. I only have 6 more minutes before my video hiccups again, so I'm going to skip number 20, and hopefully you can do 17 based on what I did for 16 and 18, and hopefully you can do 19 for what I did in 16 and 18. 20 is going to work exactly the same way as 16 and 18. Hopefully 2 of those is enough. I'm going to skip down to the bottom of the section, and you won't even know if you didn't print it out, but I added these after writing the section. I didn't want to renumber the whole section, and these fit in with this group of problems. So 39 through 44 I'll do, and then the second half of the video will start at problems 21 and kind of do 21 through 38. So for problem 40, to find the limit as x goes to negative 7 of this function, I'll go 2 times negative 7 plus 1 over negative 7 plus 7, because to find any limit, my first stab is just to take the value of x, plug it in for the x's. This is going to give me negative 14 plus 1 over 0, which is negative 13 over 0. When I'm trying to find the limit of a fraction, and I get a 0 in the denominator and not a 0 in the numerator, that limit doesn't exist, and there isn't any bit of algebra I can do to make the limit come out because it doesn't exist. So my answer to problem 40 is the limit does not exist, and I write DNE for does not exist. Alright, so 42 and 41, you should be able to do problem 39 now. It's going to work just the same way. 41 and 42 are also going to work just the same way. When I go to do problem 42, it's a limit of a fraction, and regardless of whether I'm finding the limit of a fraction or something less or more complicated, my first stab is always to plug the value for x in for the x's and do the orders of operations. So my numerator, negative 1 squared, is positive 1. 4 times negative 1 is minus 4. Minus 5 is minus 5. The denominator, negative 1 squared, is positive 1. Minus 1. I get negative 8 over 0. Again, when I have a 0 in the denominator, if I don't have a corresponding 0 in the numerator, then that limit doesn't exist. If I get a 0 over 0, then there's likely algebra I can do, either factoring and canceling or multiplying by the conjugate to make the limit pop out. But my answer for this is the limit does not exist. And then the last two problems for this section of the video, 43 and 44, I'll do 44 real quickly. To find the limit of this fraction, I'm going to plug in 1 for x, do the orders of operations, and it will tell me if I need to go further or if I have a suitable form for an answer. So 1 squared is 1. In the denominator, 1 squared is 1. Minus 3 times 1 is minus 3. Plus 2, I get negative 3 over 0. That's undefined, and it's not a 0 over 0, so there isn't anything I can do to make the limit pop out. So my answer for this is the limit does not exist.